Yes.
Are they homework assignments for effort, or are they actually graded?
Oh, by effort only.
And will the solutions be posted?
Yes, yes. A few days after it is due. All right, it's time, so let's get started. Last time, we discussed logistic regression and the loss function for logistic regression, right? The in-sample error. And we saw that for each of the sample points, we have this so-called log loss function to measure the error. Yeah? And that log loss function turns out to be simply a log of a probability, basically a log of your confidence of the label that you assign. And it has interpretations in terms of the maximum likelihood and also the cross entropy. Right? And so I hope by that kind of analysis, we are convinced that the in-sample error function for logistic regression makes sense. Yeah? It is indeed a good one to use. The only trouble is that that function does not have an easy way, does not allow us to minimize it very easily. Yeah? Does not have a closed form solution for the minimum. So we have to use a numerical method. And the numerical method that we'll use is gradient descent, which we also covered last time. And that's the form that we get at the end, right? That says that in every time step, you update this variable that you want to optimize by the negative gradient of the function at that point, at the xt location, yeah? Together with the epsilon t, which we call the learning rate, or you can just call it step size roughly, yeah? And just as a side note that here we put the xt inside the nabla just to mean this, right? That means that it is the gradient of the function at that particular point, xt. Okay? Yeah. So that's the general form of gradient descent. So let's take a look at logistic regression. What does this mean in particular? Right? So in terms of logistic regression, we want to minimize this E in. Of course, it is an average of the ENs, where EN is basically the error for each one of the sample points. And last time we saw that this EN, you can simplify it into this form. Yeah, 1 plus E and then minus yn W transpose xn, like that, right? How do we minimize this? Then using gradient descent, right? So let's find the gradient then, yeah? In the GD method, we are trying to optimize W now, right? So W is our X inside the F, E in is our F, so we are updating W to WT then the gradient at the point of Wt. Yeah, and of course this is since this is a gradient is just a derivative, and E in is a sum. Yeah, so you can move this derivative inside the sum, right? Because the derivative of gradient is a linear operation. Yeah, you can exchange the order between sum and the gradient. So times 1 over n, and then sum n over 1, or n from 1 to capital N, the gradient of what do I have? En Wt. Huh? Yeah. So therefore now our job is to find the gradient with respect to a single data point. Yeah, gradient of the error with a single point. So what is that? So let's take the gradient En W. Okay. So of course this we can read off the En. Yeah, it's a log of that 1 plus term there. So we take the gradient. Now since inside that log we have multiple variables, we use a subscript just to indicate that W is the one that we want to use as the variable for differentiation. Yeah. Right. Now you have to look for the gradient of this thing. Oh, there's a log I missed, right? Yeah. Sorry about that. Log. Okay. How do you take the gradient? Now, you can just use the general formulas. So, if you remember your one variable derivatives, derivative of a log is simply 1 over whatever that's inside, right? So that gets carried over to multidimensional derivative of the gradient as well. So this is 1 plus log of, not 1 plus, 1 plus E, yeah, whatever that's inside the log, yeah? Like that. And of course, now we have to use the chain rule of differentiation. That means we still have to take the gradient with respect to the same W of whatever that's inside. So 1 plus E minus Yn W, like that, yeah? And one more step. Now is the derivative of 1 plus something, the constant, the derivative of the constant 1 is 0, so you can get rid of that. So you have gradient of the E. Just think about the derivative of E, right? Derivative of E to something, you get the same thing, right? Same derivative of E of x, it's just E of x. So therefore, this is just minus Yn. Yeah, this is from the derivative of E. But then, again, we have to use the chain rule of differentiation. Yeah, whatever that's inside the exponent. Yeah. Oh yeah. I just now forgot the log. Now I forgot the E. Thank you very much. Yeah. Of course, E to the something. Yeah. Now, this E to the minus. And then there's E to the minus, I can divide them both in the numerator and the denominator, right? That way we can get rid of the numerator. So it becomes 1, and then at the bottom I have 1, and then the positive exponent. I'll just simplify this a little bit first. 1 plus E, now it's positive. Right? Yeah, there's a 1 there, but then I'm going to put this derivative of this onto the numerator. Well, what is the derivative of this? This is just a linear term, right? Linear with respect to W, yeah? So when you take the derivative of something that's linear, you just get the coefficient out, yeah? Again, this formula turns out to gets carried over to multidimensional derivative as well. So this simply is minus yn, there's minus, yeah, minus yn, and then just xn, yeah, just the constant multiplying the w. Okay, then we're done. So this is the gradient at this point, at any given point. Yeah, you substitute back into this formula. Now you can run your gradient descent algorithm until convergence. Yeah, okay, then you can solve the logistic regression. And so once we have this learning algorithm, basically, yeah, so we have completely defined logistic regression, right? We have the model, we have the hypothesis, we have the training data set, and then we have the algorithm to find the optimal model at the end, optimal hypothesis, W, yeah, just keep iterating until convergence, okay? Fortunately, this one is a convex function in W, yeah? So whenever we have a convex function, we know that gradient descent will eventually goes to the bottom, yeah? We get to the optimal point, yeah? We're going to talk about what happens when you have functions that are not convex, yeah? For example, neural networks, yeah? We're going to deal with that later. In fact, we'll start tomorrow, yeah. But as a side note, since today we have a bit time, there are students who ask, how do we know this, this kind of formulas can be used, okay? So for complicated cases, I would say, yeah, just go by the formula that you have seen. You can look up in textbooks and just like your integration tables and derivative tables, right? You can look them up, and the mathematicians have already proved them, yeah, for us. But I think maybe it's beneficial for us to, solve some of these simpler derivatives or gradients, just to maybe get a better feeling about what is the gradient, what does the gradient mean, and how is it properly defined, yeah? So, for example, let's look at the last step here. How do we know that when we take the gradient of this kind of inner product, we just get xn, yeah? Just get that other vector out, okay? How do we know that? So one way to know, well, let's take a gradient, right? The gradient of this multiplying some kind of a x, yeah, whatever xn it can be, right? We want to show that this is equal to the vector x, right? Now, a gradient, remember, is a vector of the partial derivatives, right? So therefore, to find out what this is, we just need to find out each element, what it is. Let's say the case element, yeah? The notation for that, it's a common notation, is this, bracket like that, and then k like that. So this is the case element of the vector, okay? By definition, this case element of the vector is simply the partial derivative with respect to wk, right? So this partial derivative of this inner product with respect to wk. Okay. What is this equal to? Anyone? Everyone should be able to tell me, right? This is high school stuff. If you understand your inner products well, yeah? What is this equal to? Yeah, yeah. This is just a weighted sum of w's weighted by xk's, right? So when you take partial derivative with respect to the k's w, the ones that are not equal to k would be 0 because they're constants with respect to wk. The rest, only one term depends on wk, yeah? And that term, the coefficient is simply xk. Therefore, this is equal to xk, yeah? And just by the definition of gradient. And therefore, I know that then the whole gradient is simply you stack these xk's together. Right? So this is equal to simply the whole vector of x, right? Yeah? And that's how you know. You can derive this formula yourself, yeah, for the gradients. Another one, let's look at the other line. So when I take the gradient of e to the something, yeah? Do I get just the same e to the something multiplying whatever that you have to take by the chain rule, yeah? So let's take a look at that. So we're talking about this one, the gradient of e w transpose x, like that. Again, let's look at the case element. Yeah, it is, again, this partial e partial xk. Oh, no, wk. partial WK, like that. What is this equal to? Well, now you're just converting it to a single variable derivative. Yeah, again, something you have done in high school, just the same E, right? Doesn't matter what's inside the exponent, just exact copy, right? And then you have to run the chain rule of differentiation. So now you have partial of this inner product, partial WK. Yeah? Right? And of course, we already know how to do this partial, which is right above, right? This is xk. Yeah? But here, for this case, I can just keep it as it is. And this would tell us already that this whole vector, E is equal to, you stack them all up, right? When you stack them up, this E to the something is still just a constant that you pull out in front. And then whatever that's left is just a whole vector of those partial derivatives. What is the whole vector of those partial derivatives? Not vector, no, well, yeah, it's vector x, but another way to say this by definition, this is just a gradient with respect to the whole W vector, right? So this is the gradient with respect to W of that. Just like that, yeah? And that's how we get to the previous step, yeah? If you remember, we have a step like that before, yeah? So we have that gradient to the E something, and then we get gradient of that. The yn is simply constant that you can just insert anytime that you want. Doesn't matter. Yeah. So this is just two examples to show you that you can derive this formula yourself if you're patient enough. I think half of you have already gone to the tutorial today where the TA explained even a more complicated case, right? I hate that kind of cases because it's my mind is always has trouble visualizing the matrices and turning upside and right side and so on. So I would think for a case like that, just look it up in the table, right? I would think I'm not going to ask you to do that kind of derivation, yeah? But the simple ones, you should be able to do it yourself, yeah? Yes?
Sorry, so our goal is to minimize the error function.
Yes.
And in order to get that, we have to get to a minimized gradient that's almost close to 0.
That's right.
So my question is based on the formula that we got for the gradient descent. Doesn't that imply that the higher the value of the weights is, the better? Like the higher value of W would give us a number closer to 0.
Yes, we discussed that last time, right? For the logistic regression, the pure form, you can scale the W any way you want. The line will not change, but your loss function, the loss value changes. So therefore, this is not the best way to formulate things. Yeah, you want to, in general, you can say, I want to set the norm of W to be 1, fix that to be 1, and then optimize the W values. Yeah, or you use the regularization, right? So that you limit.
Yeah, remember we talked about it, but like then if that's the case, then how do we imply it in the algorithm that it doesn't have to like go for like the maximum value?
Yeah, so in the algorithm, you have to, in general, you have to run this. Before you run this, you have to add lambda times the norm of W. When you run that, then you always converge to a unique solution. Yeah. Either regularization or you limit it to a constrained set. Okay, so that's the how you use gradient descent to solve the logistic regression problem. Okay. So this way of solving the problem requires you to find this gradient for every single sample point that you have in your training set, right? Because this is the average over all sample points, or n of them. Most of the real-life problems, the n is huge, yeah? Modern problems, it's big data problems. So n, 10,000, 100,000, millions. And for the GPT, those you're probably talking about billions and trillions. Okay? That number is too big if you have to take this gradient all the time for every single point that you have. Yeah, and then this is for every iteration, right? Remember, you still have to iterate many times until convergence. Okay? So this turns out to be too cost inefficient, yeah, too costly. In reality, we don't use this GD method. We use a more computation efficient method called stochastic gradient descent. I hope you have maybe heard of this from other courses. Yeah? Stochastic gradient descent. What does it do? Why is it stochastic? Let's take a look. Stochastic basically just means random. Yeah? Nothing's mysterious about this term. Yeah? So random gradient descent, if you will. Okay. Just to reiterate, for a regular gradient descent, we're saying that, well, we do this t plus 1, and then you update it from wt by the gradient of the entire E in, which is an average of all n samples. In stochastic gradient descent, you don't take all of the samples, you just take one sample. You randomly choose one sample, okay? That's why it's random gradient descent or stochastic gradient descent, okay? So at each iteration, just select, let's say, uniformly at random. Let's say the nth example that you have among your data set. So it's the index is 1 to n, right? Just pick one of them at random, toss a coin or whatever. And then you set the, you just use the you just use the gradient of that sample to update. Everything else is the same. Okay. Clearly, this is more efficient. Just do it once instead of n times. Yes.
Oh, yes.
Yeah. Okay. Yeah. But the question is, does it really work, right? I mean, this is very different from gradient descent. Gradient descent we understand because that direction, E in is the best direction to go. Yeah. So there's understanding that going towards this direction is the steepest descent direction. Yeah. But it is a known fact. One can prove, it has been proven, that it does converge, well, for the convex case anyways, converges to the minimum under some very mild conditions. So in general, you can safely say that, well, in my practical problem, I can use this SGD, and I can expect that I will converge to the optimum, okay, for convex problems. The mild conditions include, for example, the curve has to have a certain smoothness, for example. Yeah. Or there are different versions of this theorem that says it converges to optimal, okay, depending on whether it is just convex or so-called strictly convex or strongly convex. Yeah, that kind of different conditions. So it's a bit complicated, you know, what those conditions are, because there are multiple versions. For this course, we don't have to worry about it. Yeah, just to say that, yeah, whenever we have a convex problem, most likely we're going to run this SGD will be fine. Okay. Yes.
I'm wondering how sparsity affects whether we use gradients and stochastic gradient, because I'm just thinking if we have, let's say, a sparse weight vector, I'm assuming we wouldn't have to take into account all the points, let's say, in.
What do you mean by sparse weight vector?
Like if there's a lot of zero weights.
Okay, that's irrelevant. That's a different issue. Okay, that's not related really. Yes. Under mild conditions, yeah. Mild conditions. Yeah.
No, I mean like the word between minimum and mild.
Oh, under. Okay. Yeah. Here we go. Anyway. So again, we don't have to worry about the proof. We also don't have to worry about a very precise statement about this. Just know that it works. Maybe one thing that we want to maybe know as a intuition, you know, why this is okay. Yeah. So let's take a look at the expectation of this gradient with respect to a single sample. So expectation of the gradient for this one example, let's say at step t, doesn't matter, yeah. For any w will work. Yeah. How do we find this expectation of this? First of all, I forgot. I can take expectation because this thing is random. Are you convinced that this thing is random? Where's the randomness coming from? Yeah, we're picking a random data point. Yeah, you know, every time that you do this, you get a different answer, right? You get a different direction. Yeah, this is a whole vector. Yeah, remember this vector points at a certain direction, right? Yeah, it is actually the best direction with respect to that particular sample point. So every time we pick, we get a different answer. So it's a random thing. So this is called stochastic gradient descent. But then it's a random thing. Then we can look at the mean value of this random thing. Yeah, this random vector. What is the mean value? Yes. That's the E expectation. What does expectation mean? It is the mean value of a random variable. Yeah, expectation is the same as the mean. It's also called the average of a random variable, loosely speaking. Okay. So how do we find the expectation? Now ECE 302, everyone should know this is a basic ECE 302. How do you find the expectation of a random variable? It is a weighted sum of what? Huh? Yeah, weighted sum of the outcomes weighted by the probabilities of those outcomes. Yeah, weighted sum of the outcomes weighted by the probability of the outcomes. So this will be weighted sum, so by the probability. So the point that we pick can be equal to 1, right? In that case, the outcome is simply the gradient with respect to the first. You know what? I'm not going to write t because I have too many w's. Okay, it doesn't matter what t is, right? Just write w. Yeah, easier. Yep. First one, and then if you pick the second one with the certain probability n equals 2, you have another one, right? All together, you have n of them. So at the end, you have probability that you pick the nth one by chance. In that case, you get the gradient with respect to the nth example. Yeah. Okay, that's the expectation. Everyone okay with this? Everyone should be very, very comfortable with probability. Okay. Yeah. It's one of the most important courses in engineering, right? What is this equal to? How do we simplify this? What is the probability that n equals to 1? 1 over n, right? Because we pick these samples uniformly, yeah? They all have the same probability, so 1 over n, yeah? Every single one of these probabilities is 1 over n, yeah? I can just take the 1 over n out, yeah? I can factor it out. So this is 1 over n summation n equals to, I should say I just to be, because I don't want to use n, I already use n as the random variable, yeah? So I want to use I. Gradient. Yeah, in fact, my notes so that I can go to correct it myself. Yeah. What is this equal to? Well, E in, right? By definition. Oops, no, nabla E in, the gradient of E in. At W. Okay, what does this mean? The mean value of our random vector is equal to this vector that we should have used, right? If we do proper gradient descent, we should have used this one. But right now we use that one. It's a randomized version of this. Yes?
Is the assumption that the probabilities are uniformly random?
Yes, remember we said we choose them uniformly at random. Yeah. So this turns out to be just a noisy estimation of the gradient that we should have used. Yeah. Another way we can say, well, this any random quantity can be viewed as its mean value plus some noise, right? Yeah. So now we have shown that the mean value is actually this nabla E in. Yeah. So therefore, this one is simply just a noisy version of nabla E in, the gradient of E in. Yeah. So this is E in plus some noise. So, in fact, this is a noisy version, but it is unbiased, yeah, because the mean value, you hit the right mean value. The term in statistics is called unbiased, right? Estimate of which is the true gradient, of course, yeah, gradient. E in, now by E in is the true gradient, yeah. So it turns out that even though we don't go exactly every step, we don't go in the right gradient descent direction. At one step we go this way, another step we go another way. On average, we hit the right direction, yeah. So therefore, intuitively, yeah, you are roughly in the right direction, yeah. So that's why it works intuitively, yeah. Of course, to prove that it really works, you have to go through all the math and show that it converges nicely to the minimum and so on, okay. All right, so is this a convincing case for SGD that it works? Yeah. Okay. You will have a chance to program your own SGD, yeah, in the programming assignment, in the second one, I think. So second note is that, well, correspondingly, the regular GD is also called a full GD, yeah, because it uses all of your data points to calculate the gradient, yeah. Sometimes it's also called batch GD. Your entire batch of data that you have, you apply it, yeah. So what is the complexity of this? This method per iteration. It's what is the big O for the complexity? Yeah, you have n, right? Yeah, you have n, and then every time you have to take d partial derivatives. Yeah, if the length of the w is d plus 1, right? So big O of d derivatives. Yeah, so therefore the complexity is m times d, number of derivatives. Yeah? So per iteration. To compute E in. Yeah. Of course, n is large in reality. Yeah, n is large in big data. Another point is that gradient is actually hard to find in general, or derivative, hard to compute in general. Now, in the case of logistic regression, it's okay because you have a closed form expression for the gradient. You just substitute and then calculate. That's very fast. But turns out that for things like neural network, taking the derivative is non-trivial. Yeah. In fact, one of the big reasons why we were not able to use neural networks for so long, even though people knew about neural networks since the 1950s, yeah, we were not able to do any computation with it because we did not find a good way to calculate the gradient of neural networks. Not until early 90s. Yeah, we'll talk about that when we get there. Yeah, so gradient in general, gradient calculation is hard. Yeah, and so this is very computationally expensive, and that's why we want to use SGD. So SGD, of course, is a OD only, right? Every time you just pick one. Yeah, that means what? For the same complexity, if you compare these two with the same complexity, I can do n times the number of iterations, right? Now, for sure, every iteration, I don't go very precise step, yeah? I go a bit away from the right path, yeah? But I can go many more steps, n times more, yeah? N is huge, yeah? So, and then I know that on average, I'm going in the right direction, Okay? So it turns out that this one numerically works better than the other one. Okay? There's a good reason for this. One reason is that your M data points in big data, usually there are some redundancies. You don't have to use all of them to find this right direction. Okay? So it turns out that it's better to go more steps, and each time is not very precise, than using all of the data to compute, do a lot of intensive computation to find the exact path. Okay? Because you don't really need to have n data points, really, yeah, in the big data to go just one step. Okay? So it turns out that one point is better than using all of them in general. Okay? So let's say can do or can go many more iterations, n times more, in fact. Yeah? The point is often there is high redundancy in the data anyways. Yeah. So redundancy. So let's say no need to use all data points in each step. And for sure, you get a very, very precise step to go forward when you use all of the data points. But it's a not worthy trade-off, yeah, in terms of accuracy at the end and the complexity that you have to pay. Okay. Now, talking about the trade-off between accuracy and complexity trade-off, for now, we only see the two extreme points, right? Either you use all of them, or you just use one. Clearly, there's something in the middle, yeah? As in all real-life problems, the middle solution usually is the better one, yeah? So in fact, that's what we do in real-life problems. We don't do this single one. We don't use all of them. We go somewhere in the middle. And this is called mini-batch SGD. And this is the most common thing that we do, mini-batch. And this is compared with the batch GD or the full GD or full batch GD. Different names, doesn't matter, yeah? So this mini-batch. So at each iteration, instead of just using a single sample, we choose a small subset of the samples. Let's say M of them, okay? Each iteration, we select M examples uniformly at random. Yeah, let's call it x1. I'll put a bracket around these numbers because these are not their natural indexes, right? These are just your randomly chosen points. We index them from 1 to m. Yeah? And then, of course, now you update your W. Instead of the average of the entire full batch, I take the average of this mini batch. Yeah? Let me put this on top so that I get the average. 1 over m, and then I goes from 1 to m, yeah? And you have the en, not en, ei. Yeah? I should put a bracket like that because that's the indicating the ith one that we pick. Yeah? What is the benefit of doing this compared with SGD? Yeah? That's right, yeah. This is averaging, right? We're averaging out some noise. Instead of a single point, it's more noisy. Now we take the average, we reduce the noise. Yeah.
I'm just curious, something like mini batch, is there maybe a version of it where I guess you make informed decisions using maybe heuristics about which examples you choose? Like if, for instance, you know that if you choose
Yeah.
points that you wouldn't consider it in use
Yeah.
only use.
Yes. First of all, we have to be very careful about choosing data points. This is called data snooping. And you don't really want to really specifically choose data for a certain purpose, because that might mess up your generalization later. Yeah. So usually uniform is the best way. You just don't care which one I pick. Whatever nature gives me, I pick it. Therefore, because I assume that later when I go out in the real world, also nature gives me data points in the same process. Yeah. But if you here, when you do training, you pick and choose, you take the risk of, yeah. But there probably are methods, especially in federated learning, when you have multiple devices each holding a subset of the data, you want to pick and choose a little bit for other reasons. But that's a bit too much for this course. Yeah. So for now, yeah, uniform pick, and then by doing this, we have a less noisy estimate. Yeah, less noisy. Still unbiased, by the way. It's very easy, right, to show that the expected value of this average is still the same, of course, right? It's a less noisy and also unbiased estimate. Yes, yeah. In probability, if you remember, if you decide the random variables, the variance decreases inversely proportional to m. Right? Yeah, you probably usually the last 2 weeks of the EC 302 course, when you have a sequence of random variables, that's where you learn about it. Yeah. The variance of this average goes down inversely proportional to m. Another benefit of this is that even though, of course, you have to do more work, right? You have to, now your complexity is m times more, but then in modern computers, you almost always have multiple cores. Or if you're in a data center, you have multiple processors. You can run this in parallel anyways, right? This m gradients can be run in parallel. Yeah? If you already have, say, my laptop has 8 cores, why not just choose m equals 8? Then my speed would be the same as you just processing one data point at a time. Yeah, I'm not wasting any time. Well, for sure, I pay more electricity to process it. You have to pay for that. It's no free lunch, but the speed of training, doesn't hurt. So a big benefit of this mini batch is actually in terms of parallelization. Parallelization across multiple processors. Yeah, that's a very important thing. Now let's look at the SGD for logistic regression. For now, just look at this a single example one, not the batch one, okay? Just there's an interesting observation that we can make here. Just like that, right? We have calculated this before. So therefore, in SGD, you say, well, I'm going to update minus, well, plus, because I can get rid of the minus sign, ym xn like this. Yeah. Just like that, right? That's how you run the SGD. Yes?
Sorry, you said that parallelization across multiple processes is possible. Is that not possible with the full batch GD?
For Blue, yeah, of course, it's possible. Yeah, of course. Yeah. Except that you wouldn't have millions of processors at the same time. So usually you pick m to be maybe equal to the number of processors. Yeah. Okay. So one thing interesting here is that you're deciding a line W, right? So eventually this line, you're using it for classification, right? So and then this line, one side is plus, the other side is minus. Yeah, right? Because that's the data that you get. That's the labels that you have for your training data. So we could use logistic regression for linear classification, right? We just design this line. the whole result was this line will be better than the linear classification. The other method that we use the line before, as we discussed before. So we can say, suppose we use, consider this W for classification. Then now we have two methods, right? We can use the logistic regression method to find the line, or we can use the PLA method, the perceptron learning algorithm, right? We have two methods for now to draw this line. Interestingly, there is a strong connection between those two, okay? Let's take a look here. Let's look at the SGD method for logistic regression. What happens? So now if xn, yn is misclassified, what happens? Well, we know that from our previous analysis, that means that this is less than equal to 0, right? Right? This product is less than equal to 0, then we say that it's misclassified. Yeah? If it's strictly greater than 0, then it's a correctly classified point, yeah? From what we have done in the linear classification case. If this is smaller than 0, what about, and if we look at the SGD formula, right, over there, we have e to this product, right? It's an e to something negative. It's something small, right? So e of yn is small. Yeah? That means that update, SGD update, becomes what, roughly? If that in the denominator, e to something is small, then denominator is just 1. Yeah? So you have simply yn, epsilon t times yn times xn. Okay? If you're sharp, then this should remind you of PLA a little bit. Right? But let's take a look at the other case. What if it's correctly classified? Then this is strictly greater than 0. Yeah? And the e to the something strictly greater than 0, well, usually it's large, right? Yeah? If this is large, then our updating becomes what? If you go back to that formula. With the SGT, if the e something is large, then the denominator is very large, becomes 0, right? The ratio becomes 0. So yeah, we don't update. Also, I should say here, let's change this to approximately equal to the one above. This is also approximately equal to, because this is not exactly equal, right? But approximately equal to WT, no update. So if we compare this with our perceptron learning update, what do you see? You have just done your homework and all that, right? That update rule says that WT plus 1. In fact, there are two cases. When we describe PLA, we say, well, only if there's an error, then we update. If there's no error, we don't update. Yeah? So we can write it in two cases. Yeah? Exactly, yeah. That's right. This is what we do, right, if misclassified, yeah? The point is misclassified. And then we don't do anything if there's a point that's correctly classified, right? We just skip over that point. Right? In the algorithm, we simply say that, yeah, pick one point that's misclassified. Essentially means that if you have any point, you just search, look at your data set one by one. Is this misclassified or not? If not, throw it out, right? Pick another one. If it's misclassified, then you update. Huh? Exactly like that. If you compare with what we have in SGD for logistic regression, it's pretty much the same, yeah? Except we allow a learning rate, a step size. So this HGD method is a softer version, yeah? And the PLA can be viewed as an extreme version of logistic regression with HGD. Yeah, that's right. Epsilon is capital 1. And also here we have approximately equal to, right? It's a softer. Here it's strictly equal to. Yeah. So it's a hard 0-1 update kind of thing. Yeah. Extreme version of logistic regression. But when it's with a single point